So, what defines something as a pure substance is that it has a composition that isn't changing, or it has a formula that can be known. So, when we come up here and look at a compound like benzene, which we know to be a compound and a pure substance, it's got a certain picture of how it looks, it's got a certain structure, but more importantly, for our purposes, is that it has a formula. We can know what elements are in it and how many. And that can appear a couple ways. The molecular formula is what's usually presented to us, what's usually the most useful information. It's the actual number of each atoms. So when we're looking at each of these, we've got 6 carbons and 6 hydrogens. Sometimes, as we're figuring out what the actual formula and then ultimately the structure is, we need the empirical formula. That's based upon the law of definite proportions, which is telling us that the ratio of one element to another always has to be constant. A lot of times, based upon our data, we first start with an empirical formula and then need a little bit more to get to a molecular. So it's important as we're thinking about these, we know these definitions. Empirical formula is the ratio of all the different atoms to one another within the compound. The molecular is when we have the subscripts exactly what the subscripts are in that compound. And sometimes those two are the same. Many compounds, especially ionic compounds and some acids, have in their full form in the molecular formula already the most reduced or simplest version of the formula. But when we're getting to that, sometimes we want to know, or sometimes we're presented with what's called the percent composition. That is in terms of mass. When we're looking at formulas, the 6 and the 6 are in terms of atoms, or we can also apply that in terms of moles. That's not saying I have 6 and 6 grams, it's 6 of these and 6 of those. The percent composition is what gives us the information in terms of mass and grams. And that's where the data normally comes from in the lab. So with percent composition, we could get this data from, an experiment if we had an unknown compound, or we might already know our chemical formula. Either way, the percent is the same thing, and it's just the definition of a percent. You find the mass of the element that you're looking at over the mass of the whole compound. So we're making ratios, we're turning that into percents, and all of that percent composition, percent by mass, they can call it different things, but it is using the grams of one substance relative to the other. And that's what we would often be able to start with when we do a lab. We then want to take that and turn that into our chemical formulas. And remember, chemical formulas, those subscripts are in terms of atoms, and those atoms can also be connected to moles. So we don't want that as mass. We've got 3 steps for each of these here, and I've got a little rhyme that I've used before, but the most important thing is to think about whatever data we're given, whether it's percent, whether it's grams, whatever we have. If we want to know a formula, it has to be in terms of moles and atoms. It can be in terms of moles because a mole of carbon has 6.02 times 10 to the 23rd atoms. A mole of hydrogen has 6.02 times 10 to the 23rd atoms. So by getting the ratio of moles, we're also getting the ratio of the atoms. So if we're given a percent composition data, if we have just found it in terms of percent, we have to treat it, this one's a step I didn't fully write, as if we had a 100 gram sample. And the reason that's important is it makes kind of step 0 really easy. If something's 60% carbon and 40% hydrogen, and I had 100 grams of it, that's 60 grams of hydrogen, 60 carbon, 40 hydrogen. And that data won't even make sense if you tried to do it, but that's what that means. So we start with a mass, then we just use the molar mass of that element. And in this case, we're not dealing with diatomics. We're not talking about compounds. It's just however many grams, that element, its molar mass, its atomic masses, and think of it in terms of moles. So then we would have at least 2, but maybe 3, 4, 5, 6, 7, depending how complex our compound, different number of moles. Well, those moles are probably going to show up as decimals. So we can't just put a whole bunch of decimals as our subscripts. We need to change those or make a ratio of those. So ratios are used taking the moles of each substance by whichever one is the smallest. You get 2 or 3 values, the smallest one goes on the bottom, and then that should come out to whole numbers. Those whole numbers are the subscripts of the formula. If it's not a whole number, if it's like 0.99999, we would round that up to 1. But if it comes out to a really clear like 1.5, that would be showing, and some of the examples will have this, that for every 1 of the first element, I have 1.5 of the second. We can't have 1 atom bonded to 1.5 atoms, but we could have 2 atoms bonded to 3 atoms, which is what multiplying by whole to get whole numbers means. So in terms of a rhyme, we change our percent to mass. And in doing that, by imagining a 100-gram sample, all we're really doing is changing the percent sign to a big G, or I guess a little g. Then mass to moles, divide by smallest, multiply till whole. So percent to mass, mass to moles, divide by smallest, multiply till whole. That is what we're doing. Maybe the rhyme helps, and maybe the rhyme will be great on our first test. But when we're thinking end of the school year, if you tried to have a mnemonic device for everything we're going to learn, it might be a little tricky. The idea is convert the things to moles and then look at the ratios. And that's true for lots of different types of problem solving. That gives us our smallest ratio. If we want the real formula, we need more data. We need the molar mass of the full compound, which can be observed from a couple different sets of data. We don't need to care where it came from. It would have to be given to us. So we take the molar mass of the whole compound divided by the molar mass of the formula we just found. When you divide those, it'll be big number over small, or maybe a number over itself, and that'll determine the ratio. That has to come out to a whole number. It can't be a 1.5 or whatever. It just doesn't work that way. So it's going to come out as 1, 2, 3, 4, 5, a whole number. That just means that that's how much heavier the real compound is than the formula we used. So then we multiply all our subscripts by that. Up here, the empirical formula, that would have a molar mass of about 13. So what we would do would be dividing a number that's like in the high 70s, about 80 divided by 13 comes out to right around 6. That means the full compound is 6 times heavier than that ratio, of that 1-to-1 ratio right there. This is something that a little bit of practice and repetition is huge for, and really thinking about the why instead of just memorizing the process is super helpful.